We have about 25 minutes. I have to bring you to the present, so that's not much time. But I've picked out a few things. It's mostly pictures, so it's not going to be very taxing. So there's this quasi-biweekly oscillation. It's about 14-day period in the tropical atmosphere and also in the ocean. That's what the talk is about. I will show you two regions where this is prominently seen. One is the equatorial Indian Ocean and one is the Bay of Bengal. So the shallow water equations, in 1966, Matsuno gave a complete theoretical prediction saying there should be these classes of waves which are trapped at the equator, and that's the solution where V is north-south velocity, Y is north-south coordinate, and there is this Gaussian, and that's the equatorial trapping, and there are the Hermite polynomials. So you have many modes, each one has a certain shape in Y, but in the X direction, in the east-west direction, these waves can go freely around the Earth in the atmosphere, but in the ocean, of course, broken up into basins. So there are four kinds of waves. I've not shown the gravity wave. They have different symmetry properties. The Rossby wave has maximum east-west velocity at the equator, 0 north-south velocity, and maximum V away from the equator at about 1 Rossby radius. The mixed Rossby gravity wave or Yanai wave has maximum V at the equator, 0 U, and maximum U away from the equator. And we'll see examples of these waves. These are the two relevant to our story. That's Matsuno right after his PhD defense. And he wrote up a paper based on his PhD work. The Rossby wave structure was predicted in this beautiful paper. It's got counter-rotating vortices on either side of the equator. And that's the simplest possible equatorially trapped Rossby wave. You can have higher meridional modes. Remember those Hermite polynomials? You can have more zero crossings, both left and right. But this is the simplest one. And in this paper, it's a brilliant paper. And I like the modesty of this last sentence. It would be interesting if we find trapped waves in the actual atmosphere. It's hard to find a paper that ends on such a modest note these days. And indeed, there are these waves wherever you look in the atmosphere and ocean. So that's the symmetric part of the brightness temperature spectrum. If you assume the tops of the clouds are radiating like black body, you can work out the temperature from the satellite measurements of radiation. And so that's the Kelvin wave. And these are the Rossby waves. They move westward. Phase moves westward, and zonal wave number 5 would mean 40,000 kilometers, 5 waves, so that's about 8,000 kilometers. These are observations from satellites in the tropics, 15 south, 15 north. There's this thing called the Madden-Julian oscillation that's not predicted by the linear shallow water theory. The antisymmetric part of the spectrum has these mixed Rossby gravity waves. Energy always moves east, as you can see from the slope of this line, and phase moves to the west. On the left of zero, phase moves to the east, the right of zero. So this is from observations, and these lines are what was essentially predicted in Matsuno's work. So what's this 14-day oscillation? It was noticed about 50 years ago. Mid-70s. This is a picture of sea level pressure in July. India is here. That's the Mascarene high. That's the monsoon trough. Low pressure here, high pressure here. And Krishnamurti, who was one of the pioneers of monsoon meteorology, quasi-biweekly oscillation in almost all elements of the monsoon system. So that's rainfall over central India in 1967, for example. You can see these spells of heavier than average rain and these dry spells from May through September. And that's the spectrum of the monsoon rainfall. And Krishnamurti has marked a little wiggle at the 15-day period. In this form, the spectrum is a variance preserving. So area under the curve actually is proportional to the power in that frequency. Monsoon trough pressure is got this 15-day oscillation again. Mascarene high pressure has this 15-day. And at the end of the paper, Krishnamurthy and Bhalme offer possible origin of quasi-biweekly planetary scale propagating waves. Surface heat flux changes atmospheric stability and clouds, and then the clouds change atmospheric stability and surface heat flux. So if you haven't allowed sunlight to reach the ocean surface for some time, then the atmosphere becomes stable, and then the convection stops. And what are these planetary scale propagating waves? They were aware of Matsuno's work. So you have these dynamical entities, the Rossby wave, for example, moving westward, but frictional convergence near the surface, little bit of lift in the vorticity part of the Rossby wave, that is enough to couple it to the clouds. So this is from Chatterjee and Goswami. 2004, we have moved many years now. They gave a possible explanation of these quasi-biweekly waves. If you have a model which has moisture, which has frictional convergence in the boundary layer, then you can pick out an unstable mode. The scale selection is about 6,000 kilometers and 15 days. So this double cell structure, one centered at 15 to 20 north and one at the equator, both cells move coherently westward, is a picture from a classic paper, Chen and Chen, about the summertime Rossby wave. You can see the Rossby wave here. It's very large scale. That's half a wavelength. There's counter-rotating vortices, but this time they're not symmetric about the equator. Perhaps the moisture field renders it, the dynamical equator is somewhere here. There's this tilted line at about 10 degrees north. On the east, it's at about 5 degrees. And that's the spectrum, and there is this quasi-biweekly period right here, this part of the spectrum. There are also lower frequency. Frederick Schott, 1991, installed these current meters south of Sri Lanka. So there are these 3 current meters measuring ocean currents this time. And this is the time series of upper ocean volume transport in 10 to the power 6 cubic meters per second across this array. And there is this expected seasonality. So in summer, the flow is from west to east, from the Arabian Sea to Bay of Bengal. In winter, the flow is from east to west across this array. And that's what you see here. But on top of these, this was not expected, these 15-day oscillations in the transport. And at that time, it was a perfectly reasonable hypothesis that these things are coastally trapped Kelvin waves that come from Bay of Bengal, move south of Sri Lanka, and pass the array. And that's giving rise to these 15-day oscillations. But it took a while for connection between this Rossby wave and the equatorial fluctuations to become clear. So when the quick scatterometer winds became available, we took a simple configuration of the GFDL ocean model and forced it with quick scat winds. We started from rest and just forced with quick scat winds for a few years. And in response to those Rossby waves in the atmosphere, the ocean develops these mixed Rossby gravity waves. So that's the wavelength. V velocity is maximum at the equator. U is antisymmetric. If there's upwelling on one side of the equator, there's downwelling on the other. So that's exactly what you would expect. If you put this vortex on the equator, at this place and this place, you would generate V velocity in the ocean because F is 0 at the equator. But on either side of the equator, the curl of wind stress is positive and negative. So you'd get upwelling on one side, downwelling. As this structure moves, this structure also moves. And if these currents move past Sri Lanka, that's what gives you those big fluctuations in the transport. And this is a resonant response because that's the velocity spectrum in the ocean. And the spectrum of wind stress is broadband. It has this little 15-day variability, and that's picked up by the ocean. It's a resonant response. Then these mixed Rossby gravity waves move, and that's the westward movement. Time goes this way. And that's longitude, eastern side of the Indian Ocean, western side of the Indian Ocean. And these are the very regular mixed Rossby gravity waves. They also propagate down. And you can see this 500 meters depth in the model, in the quick scat simulation. Phase going up is equivalent to energy going down into the ocean. If you draw the same sort of spectrum, Matsuno sort of spectrum for the ocean velocity, that's what it looks like. So that's the mixed Rossby gravity wave. The maximum power is here at 2 weeks and 3,000 to about 6,000 kilometer wavelength. So that's wave number, that's frequency. Time period in days is mentioned here. Wavelength in thousands of kilometers mentioned. So that's the signal that we are seeing. And that's what Short saw in his current meter measurements. You will see this, of course, in the symmetric part of north-south velocity and also in the antisymmetric part of the east-west velocity. Same signal. So the 15-day Rossby wave in the atmosphere is driving these mixed Rossby gravity waves. And crucial is that the line of symmetry of that atmospheric Rossby wave is not at the equator. Sometimes north of the equator, in summer, for example, sometimes south of the equator. You need that vortex to be straddling the equator for this to happen. So this is the general circulation model driven by the quick scat winds. And this is the Lakshadweep ridge, for example. And this is the same thing in a linear, continuously stratified model. In the GCM, you have topography. So this is the shadow of those MRG waves. So they propagate this way, bounce off the surface, and you can see amplified MRG at some places. In the GCM, on this side of topography is the shadow region of this energy cannot reach. In recent years, this has been taken very far. And for example, by looking at the rate of change of sea level from satellites, you can see MRG waves of different mode numbers. These are vertical modes, N1, 2, 3. And you can see that the wave can be generated both by the shear of the zonal winds about the equator and also directly by the V winds, and the group propagates to them. So we are in 2020 and 2021. Now, around the same time, I said Bay of Bengal. We see the signal in the Bay of Bengal as well. We were doing these field campaigns in the Bay of Bengal, and we had put these moorings. This is from an older field campaign. This is the vertical structure of salinity at 2 stations in the northern Bay of Bengal. The salinity is very low near the top, and then there are these haloclines, and salinity actually controls the density, so these are the pycnoclines as well. So very sharp n squared maximum here and here. We don't really understand what this deeper level, so this halocline, the second halocline, very often seen, we don't really understand what it is. It could be from last year's river water, or it could be from the Irrawaddy. We know that in winter, water from the Irrawaddy comes to the North Bay of Bengal. This one is from this season's rainfall and Ganga Brahmaputra discharge. Global ocean mean salinity is about 35. At 100 meters, that's what you see. This is the World Ocean Atlas version of these haloclines. Mooring data for 4 years, all summer, May through October, I've shown here. That's SST on top, and that's salinity below. Very often see 15-day fluctuations in sea surface temperature, 30-day fluctuations. Sometimes there are these intraseasonal oscillations which are longer, maybe 45 days. In salinity, also you see these 30 and 45-day fluctuations, but 15 days is common, especially in 2015, which I'll be spending a little time. There's 1, 2, 3 pulses of very fresh water. Salinity scale is over here. These come from the river. These come from the Ganga Brahmaputra. Mooring is about 500 kilometers to the south. You get these pulses of river water at the mooring. So if you take several years of mooring data and do a variance preserving spectrum, in salinity you get a very neat biweekly signal. In temperature also, but it's dominated. Sea surface temperature responds to longer period forcing, and therefore it's dominated by the 30 to 60 day variance. So in 2015, we had a mooring here and 2 other moorings maintained by NIOT. So there's a cluster of 3 moorings. I'll show you very soon what happens. We have the SMAP satellite sea surface salinity. This is a brilliant satellite. It gives you sea surface salinity from changes in the microwave emissivity of seawater, which is a slightly conducting fluid. This measurement is so hard to make that to get these salinities, you had to subtract out the galactic microwave radiation reflected from the ocean surface. It took a long while to develop this satellite. And there's this reanalysis, about 8 kilometers, Nemo ocean posed by ECMWF surface fluxes. It's available in the public domain from Europeans. So that's the Woods Hole oceanographic mooring, 1 meter salinity in black. Time goes this way, July, August, September, and October. And also from SMAP and also from the reanalysis, 0.5 meter depth salinity. So they all show these 3 pulses of river water. That's salinity at 18 meters. Nothing much happens. At this time, there was a cyclonic storm which has mixed down the ocean to about 18 meters depth. But after that, it's very stratified. There's a movie here. I don't think it's going to play. So these are pictures about 7 days apart. The mooring is here. That purple dot is our mooring. The velocities are from sea surface height, from Aviso. Geostrophic currents deduced from sea surface height. The colors here are salinity. So these are high salinity, that's the river water. On 8th August, it's touching the mooring. And 8 days later, it's moved far away from the mooring. 8 days later, again, it's come back to the mooring. So that's the river water moving, sloshing back and forth on the surface of the ocean. Once again, on 10 September, it's here. So that's what you see. 3 times the river water reaches the mooring. Why does it do this? You can understand that if there is river water, the Ganga Brahmaputra is here. If there's river water, it's going to be drawn out into the center of the Bay of Bengal because of the flow in these 2 counter-rotating vortices. So you can see the blue colors here. It is drawn out. You can see that mushroom shape characteristic of this stirring of river water. But why does it move back? The eddies don't change that much in the interim. The river water moves back. So if there are 3 moorings here, 2 NIOT, National Institute of Ocean Technology moorings, and there's a Woods Hole mooring. So during the freshening times, these are the velocities in red in the ocean, and that arrow is 0.3 meters per second. And these are the winds. The winds are weak, and it's the eddy flow that's bringing the river water. Second episode of freshening and the third episode of freshening. Weak wind speeds, 2 to 5 meters per second. When the monsoon winds pick up, so monsoon has this active break cycle. In 2015, the 15-day oscillation happened to be pronounced. When the winds pick up, that's the black vectors. And this is what you measure in the ocean. So take a look at this one. It's easier to understand. And that's the winds, and that's the current. So that's dominated by the directly wind-forced part. If this was steady state, we would call it Ekman flow. With shallow layer of river water, all the wind momentum is being put into that shallow layer, 5 meters, 10 meters deep, and you can get a swift Ekman current. These currents would be easily 30, 40 centimeters per second. So that's what's happening. You have, and these two, the black and the red line showing the same thing as a function of time. Salinity is in red and wind speed is in. So when the winds pick up, you have high salinity, and because the river water is moving away. When the winds are weak, let's say here, 2 meters per second, the river water has come to the mooring. There's probably another part of the story which we don't understand yet. Is that, so there's this thin layer of river water and it's confined to the north and east Bay of Bengal. Is there a buoyancy-driven flow that brings it back? Even without those 2 eddies, maybe that plume of light water would have come back to the interior. We don't know. We tried doing some estimates, the velocities come out to be 30, 40 centimeters per second in either case. So here's what happens in summer of 2015. Those Rossby waves come from the Pacific and they move westwards. So this is trim rainfall, satellite rainfall, July through September. in 2015 as a function of latitude and longitude. This is dateline. So it's coming all the way from Central Pacific, and the Bay of Bengal is here. And you see these 1, 2, 3 episodes, and the period between them is 15 days. And that's the V winds from the MERA 2 reanalysis. The same 3 lines have been drawn here. And so that's the V wind. I've shown only the positives in color, so from 0 to 10 meters per second. So you see this, the wind and the rain are moving together in those Rossby waves, and that's what's giving you the signal in the Bay of Bengal. What else happens? There is also variation in sea level. So that's Chittagong tide gauge in red. Let me go back 2 slides. Okay, Chittagong is about here, somewhere here. That's in Bangladesh. So that's Chittagong tide gauge data. No filtering except the tides have been removed. This is August and September. So 3 times the tide gauge shows these pulses of high sea level. That's 0 and that's 0.6 meters. These are not storm surges. These are not tides. It's just the winds, the monsoon winds increasing and falling gives rise to this nice signal in the at the Chittagong tide gauge. That's the wind stress average north of 17 degrees north in the Bay of Bengal, and that's the Chittagong tide gauge data. You see these 2 pulses. For example, this one, the sea level has risen about half a meter in 3 or 4 days. That's what the spatial structure looks like. High wind stress here from MERA 2 reanalysis. It's just 3 days apart. The difference of wind stress in these 3 days, 20th September minus 17th September. So that's the high wind stress. 0.2 newtons per meter squared here. Chittagong is there. And this is what happens in the ocean. The difference of sea level across these 3 days. So the sea level here is higher by about 20 centimeters on 20th relative to 17th. Very rapid response. And it's all got to do with this river water being moved back and forth by the monsoon winds. So I'll stop here. This is a summary. This is a shared subseasonal time scale in the tropical atmosphere and ocean. Some years it's seen very distinctly. Some places like south of Sri Lanka, it's seen very distinctly. In some other place, you might have to wait for a while before you see this clear signal coming and going. Atmospheric quasi-biweekly oscillation resembles equatorially trapped Rossby wave. The Indian Ocean, the equatorial Indian Ocean responds to the surface wind stress as resonant MRG waves, very large wavelength. Bay of Bengal salinity and sea level also respond to the quasi-biweekly wind stress variability. I'll stop here. Thank you.
Probably have time for 1 question.
Thanks. That was a nice, very convincing story. Are you sure there's no tidal spring neap cycle that has any influence on the river outflow?
We removed all tides from the Chittagong tide gauge data, every component of the tide, and that's still left over. And you can see it in the altimeter. So this is a.
I guess you could have a mixing signal that was during stronger tides. You have more dilution of the.
We checked. Oh yes, because we have this reanalysis product matches relatively well with the mooring data. The volume of fresh water, that's volume of river water floating on top of the ocean, that doesn't change. It's just a sloshing back and forth, as far as we can tell from the reanalysis. So there's probably no strong mixing, and it's probably not the spring neap cycle.
All right, let's thank Debasis again.